In this video, we will be talking about reformulations and relaxations for integer optimization, and these results are from chapter 8 of the book. The results that we will see apply to a very wide class of problems that appear especially in real-world problems. And these are problems when you have a subset of constraints that have a nice structure, while another subset of constraints have a structure that you currently don't know how to deal with. This can happen all the times, especially in real-world applications. So, for example, think about a case where you have studied for a long time a very specific problem, and at this point you know everything there is to know about it, and then suddenly your boss adds a bunch of constraints to this problem that you never dealt with before, and at this point you exactly are in this setting where you have a part of the problem that you know exactly how to deal with, and you have a new part of the problem that complicates what you knew so far. And in this chapter, we're going to discuss exactly how to approach these types of problems. In particular, we will discuss a Lagrangian approach, which exploits the structure of the nice constraints to obtain bounds on your problem, which are potentially better than those obtained with the standard LP relaxation. So let's start with the Lagrangian relaxation. Let's fix the notation for our mixed integer linear programming problem. In this problem, we have n variables, they're all non-negative, and only the first p of them are required to be integer. Then we have a polyhedral region, ax less than or equal to b, and we are maximizing an objective function cx, and we denote by zi the optimal value of this integer program. Furthermore, we always assume, as always, that all the data is rational. We immediately partition our inequality constraints into two subsystems, and we're always going to denote them by a1x less than or equal to b1 and a2x less than or equal to b2. And we're also going to use mi to denote the number of rows of the matrix AI. This partition is of course up to us. We can use any partition of this form. And based on our partition, now I want to immediately define what is the Lagrangian relaxation. So the first thing I need to do is define the following mixed integer linear set. It is essentially the mixed integer linear set of our original problem, but where we drop the inequality constraints of the red system. So as you can see, we have non-negativity on all the n variables, we have integrality on all the first p, and then we only have the constraints in green. We're now ready to define the Lagrangian relaxation. Pick any lambda in R plus m1. So this is a vector of multipliers associated with the red constraints. Then we define the Lagrangian relaxation, and it's always denoted as LR of lambda, because of course it depends on your choice of lambda, and it's defined as follows. You want to maximize over the set Q that we just defined, and your objective function is the original Cx, but since in Q we no longer have the red constraints, we are somehow adding those inequalities in the objective function as a penalty. In particular, the objective is then Cx plus lambda b1 minus a1x. So this is our definition, and I just want to give you a little bit the intuition behind this. The idea is that if you do not satisfy the red constraints, then this quantity is negative, and since lambda is non-negative, this whole part of the objective is negative, and so it drives down our objective function, making it far from optimal, since we're maximizing. Now, the optimal value of this maximization problem is denoted by ZLR of lambda. And here in the last line, we simply have the same Lagrangian relaxation, just rewritten in a way where the x variables are all together, so that it's a bit clearer what is the function that you're maximizing. In fact, such objective function is c minus lambda a1 times x, because essentially lambda b1 is a constant once you have fixed your lambda. So the definition we gave of Lagrangian relaxation applies to any partition of ax less than or equal to b in red and blue constraints. However, in practice, how should you subdivide your system into these two subsystems? Well, typically the green constraints, as the color suggests, are nice constraints in the sense that you are able to optimize any linear function over the set Q, which includes only these constraints. In fact, this allows you to evaluate ZLR lambda efficiently for any lambda. Therefore, the red constraints are viewed as the complicated constraints. So essentially, these are the constraints that you need to remove from your mixed integer linear set so that you can optimize over it efficiently. Now let us discuss a little bit the Lagrangian relaxation from a polyhedral perspective. In the first line here, I have our definition of Lagrangian relaxation that we just saw a couple of slides ago. We know very well that optimizing a linear function over a mixed integer linear set is the same as optimizing it over its convex hull. Therefore, the Lagrangian relaxation could be solved in principle by solving just this LP if we knew the convex hull of Q. But now we can analyze a little bit better the Lagrangian relaxation polyhedrali. In fact, we immediately understand that the objective value of the Lagrangian relaxation is finite if and only if for every ray of the recession cone of the convex hull of Q, we have that along that ray the objective function decreases. In formula, we look at our objective function and evaluate it on the rays. C minus lambda A1 times R must be less than or equal to 0, because otherwise, if it's greater than or equal to 0, you can travel along that ray and your objective can always go to plus infinity, since you're maximizing. In particular, now let's look instead at the extreme rays of the convex hull of Q. Then ZLR lambda is finite if and only if for every such extreme ray this condition holds. So if we substitute in this formula R to be one of these RH, we obtain exactly this inequality, which must hold for every extreme ray. Therefore, the Lagrangian bound is finite if and only if our non-negative multiplier lambda satisfies all these inequalities. And we're gonna denote this polyhedron by a capital P. Note that in this description, the variables are just lambda. Everything else is data. So A1, of course, is data. RH is just an extreme ray of the convex hull of Q, so it's data. And same goes for C. So now, assume that we satisfy these conditions. In this case, the Lagrangian bound is finite. Then what is actually the value of this Lagrangian bound? Well, then it must be the maximum of our objective function over all the vertices of the polyhedron conv Q. So denote by Vk all the extreme points of conv Q. Then the Lagrangian bound is the maximum of the objective function evaluated in the vertices plus lambda b1, which is just our constant in the objective function. And finally, this formula allows us to understand a little bit better how this function ZLR of lambda looks like. In fact, it is the maximum of a finite number of affine functions, namely the function C minus lambda A1 times Vk plus lambda B1. These are all affine functions of the variable lambda. In fact, both this term and this term is linear in lambda, and plus you have CVK, which is a constant. Now you're taking the max of all these affine functions, and so, as we have seen in chapter 2, this is a convex and piecewise linear function. The next proposition implies that the Lagrangian relaxation allows us to bound our optimal value of the original integer programming problem. In fact, this proposition says that the Lagrangian bound is greater than or equal to Zi for every lambda. Let's now prove this proposition. The first thing to observe is that we can assume that a feasible solution of the mixed integer linear programming problem exists, because otherwise we have Zi equal to minus infinity, and so of course the Lagrangian bound cannot be smaller than that. So obvious when Zi is equal to minus infinity. So we assume that a feasible solution of the original mixed integer linear programming problem exists. So how are we going to show this proposition? We pick any feasible solution of the mixed integer linear programming problem. We show that it's also feasible for the Lagrangian relaxation and that it has objective value greater than or equal to its original objective value. That's enough to prove that the Lagrangian bound is at least ZI. So let x bar be any feasible solution of the mixed integer linear program. Well, so we know x bar is in Q. Since Q is a relaxation of the mixed integer linear set of the original problem, therefore x bar is a feasible solution of the Lagrangian relaxation with multiplier lambda. Now the objective value of x bar in the Lagrangian relaxation is, just by definition, Cx bar plus lambda times B1 minus A1 x bar. Now, lambda is by definition greater than or equal to 0. And since x bar is feasible for the original program, we also have that B1 minus A1x is greater than or equal to 0. So this objective value is greater than or equal to Cx bar. So this implies that the Lagrangian bound is greater than or equal to Zi. And that's the end of our proof. So let's get back to the slides. So far, we have defined the Lagrangian relaxation for any non-negative lambda. And each one of these Lagrangian relaxations gives us an upper bound on Zi. So it's only natural to ask what is the best upper bound that we can get, meaning, of course, the smallest upper bound that we can obtain. And this leads us to the definition of Lagrangian dual, which is defined as the minimum Lagrangian bound for any lambda greater than or equal to 0. While the optimization problem is called the Lagrangian dual, the corresponding optimum objective value is denoted by ZLD. The next theorem characterizes ZLD as an optimal solution to a linear programming problem. In fact, it says that ZLD is the maximum of the original objective function Cx over the convex hull of Q intersected with the complicating constraints in red, provided that the corresponding polyhedron, which is the feasible region of this linear optimization problem, is non-empty. Now let's prove this theorem. How can we prove this theorem? So let's look at the statement for a second. So we want to show that the Lagrangian dual is equal to this linear programming problem in maximization form. As the name suggests, we're going to use duality to prove this theorem. Now, the dual of a maximization problem is a minimization problem, of course. So if ZLD was a minimization problem, we would be somewhat happy because then we could take the dual and hope that it's actually this maximization problem in the statement. However, note that ZLD is not, in its current form, a minimization problem. In fact, it is defined as the minimum of all the Lagrangian relaxations, and each one is a maximization problem. So in order to obtain that ZLD is a minimization problem, we're gonna transform every Lagrangian relaxation as a minimization problem so that ZLD, instead of being a min-max problem, will be a minimization problem. So since we're always working with the convex hull of Q and we want to use essentially linear programming, the first thing we want to do is introduce a notation for such a convex hull of Q as a matter of linear inequalities, which we can do by Meyer's theorem. So let's do that. Since A2x less than or equal to B2 is a rational system, by Mayer's theorem, there exists a system Cx less than or equal to D such that the convex hull of Q is the set of points in Rn such that Cx less than or equal to D. Great. Now let's write our Lagrangian relaxation in minimization form. So for every lambda greater than or equal to 0, we obtain ZLR lambda is equal to, so by definition it's the maximization problem with objective C minus lambda A1x plus lambda B1 over the convex hull of Q, which we then write as Cx less than or equal to D. So now this definitely looks like a linear programming problem, so we can take the dual. So this is the min over variables mu of mu d plus lambda b1 such that mu c equal to c minus lambda a1 and mu greater than or equal to 0, where the last equality follows by LP duality since Q is non-empty. At this point, we can finally write our ZLD, our Lagrangian dual, as a pure minimization problem. So it follows that ZLD is equal, so by definition it's the minimization problem over lambda of ZLR lambda for every lambda greater than or equal to 0. So now it is the minimum over lambda and mu of mu d plus lambda b1 such that lambda a1 plus mu c equal to c, lambda mu greater than or equal to 0. Let's take the dual as we discussed. The latter is the dual of the LP max Cx with a1x less than or equal to b1 and Cx less than or equal to d. And we're done. So their optimal values coincide because the primal is feasible by assumption. And that's it. Let's go back to the slides. Now that we've shown theorem 8.2, I want to briefly discuss the assumption of the theorem. Namely, we're assuming that the feasible region of this maximization problem, this set over here, is non-empty. And we saw in the proof that we in fact used this assumption. A natural question then is, do we really need this assumption for the theorem to hold? And the answer, of course, is yes. In fact, you can easily construct examples where this set is empty and where not only ZLD is different from the maximization problem over such a set, but you can actually construct example where the max is, well, of course, minus infinity because the feasible region is empty. And on the other hand, ZLD can be equal to plus infinity. In particular, in the remainder of our discussion, we will always assume that this set is non-empty so that the theorem holds. In particular, this implies that the convex hull of Q is non-empty and therefore that Q is non-empty as well. Finally, note that this assumption is, in a sense, not a big deal. The reason is that if this set is actually empty, then so was the original feasible region of your problem. In this slide, I want to discuss the relationship between our true optimal value of our integer linear programming problem, our Lagrangian dual bound, and the bound obtained from the standard linear relaxation that we denote by ZLP. So formally, ZLP is the max of Cx over the points that satisfy Ax less than or equal to b and x greater than or equal to 0. So like our original problem, but we just drop integrality constraints. We know very well that both ZLD and ZLP are upper bounds on Zi. However, it is simple to see that ZLD is always less than or equal to ZLP. To prove these inequalities, we can just compare the feasible region of the three optimization problems written as linear programming problems. So for Zi, the feasible region is the convex hull of our original mixed integer linear set, convs. For the Lagrangian dual, due to the theorem we've just seen, the feasible region is conv-q intersected with the set of non-negative x that satisfy the red system. Finally, for the LP relaxation, as we have just written, the feasible region is the non-negative vectors that satisfy Ax less than or equal to b. Now clearly S is contained in Q, it satisfies non-negativity, it satisfies the red inequalities, and it satisfies also the remaining green inequalities. Therefore, S is contained in this intersection and in this set, and since both sets are convex, they also contain convs. So it's clear that convs is contained in both these sets. On the other hand, how do these two sets on the right hand compare? Clearly, conv-q satisfies all the green inequalities. Therefore, this intersection is contained in the feasible region of the LP relaxation. So this simple comparison allows us to actually prove corollary 8.4. This corollary tells us, in other words, that the Lagrangian dual bound is always at least as good as the upper bound obtained from the standard LP relaxation. Of course, in some cases, these two bounds can coincide. For example, whenever the convex hull of Q is exactly defined by the green inequalities and non-negativity, then we obtain that the Lagrangian dual bound is equal to the linear programming bound. Recall that Q is defined exactly as the set of mixed integer points that satisfy these conditions. Therefore, asking for this condition is equivalent to asking that this system gives you a perfect formulation of the set Q. In chapter 4, we have of course seen several examples of perfect formulations. And for example, if all the variables are required to be integral, if A2 is totally unimodular and B2 is integral, then our sufficient condition is satisfied, and therefore we obtain that the Lagrangian dual bound is equal to the linear programming bound. In the next few slides, we're going to look at a specific example of a Lagrangian relaxation applied to the traveling salesman problem. And for that example, we're going to need to apply the theory that we developed in a slightly different form. Namely, some of the constraints of the mixed integer linear programming problem will be equality constraints. Therefore, let's see, in general, how the theory that we developed changes if we have some equality constraints in our original formulation. For example, think about a setting where we have that our red constraints are all at equality, while the green constraints are, as before, in the form less than or equal to. Then we define the set Q in the same exact way, and this makes sense because the inequalities that are green didn't change at all. On the other hand, the multipliers lambda will change because they were required to be non-negative and now instead they will be just free. Therefore, the Lagrangian relaxation will be defined for every lambda, and the Lagrangian dual will be the minimum over all lambda in Rm1 without the constraints that lambda has to be greater than or equal to 0. More generally, you could of course have some inequalities of the form less than or equal to in here and some equality constraints. In this setting, as you can imagine, you will have that the lambdas corresponding to the inequality constraints will have to be greater than or equal to 0, and the ones corresponding to the equality constraints will be instead free. Now that we've clarified these kind of different forms of Lagrangian duality, let's look at our example. So let's focus on the traveling salesman problem. In particular, we want to discuss the symmetric TSP problem on an undirected graph with the cost CE, as we have already discussed in chapter 2. We saw the Dantzig-Fulkerson-Johnson formulation. Recall that we have degree constraints on every node and we have subtour elimination constraints. However, note that there is a subtle difference with respect to the Dantzig-Fulkerson-Johnson formulation that we have already seen. So if you remember, in the original formulation that we have seen, here we had every subset of V that was non-empty and not equal to V. So essentially we didn't have this set minus 1. So the question is, why can we actually write down here a minus 1 without changing the formulation? Well, the reason is very simple. In fact, for every set S that is contained in the empty set and contained in V, if we take the inequality corresponding to S and the inequality corresponding to V minus S, you obtain the same exact inequality. So essentially, among these two, for every set S, you can keep only one and you can always throw away the one containing node 1. So essentially, this formulation is obtained from the original Dantzig-Fulkerson-Johnson formulation that we've already seen by just throwing away for each pair of these identical inequalities just the one containing node 1. We're gonna denote the optimal value of this problem by ISyE, as we're doing in this chapter. Before constructing a Lagrangian relaxation of this problem, I want to massage a little bit this formulation. So the first thing I want to do is rewrite the subtour elimination constraints in a slightly different way. The reason I can do that is because I have equalities that I can always use in order to essentially tilt my inequalities so that their intersection with the affine hull of the polyhedron remains the same. In particular, while the current subtour elimination constraints tell us that you must have for every set of nodes at least 2 edges leaving the set, we're going to write them in this equivalent form. In this form, we're looking at the sum of the x's for every E fully contained in the set S, and we're asking that this sum is at most the cardinality of S minus 1. It's a very good exercise to show that these inequalities are equivalent to the previous ones, and of course in order to show that you need to use the degree constraints. The next change to this formulation is in a sense trivial because we're just gonna add one constraint that is redundant. In fact, it's already implied by all our equations. In fact, if you sum the degree constraints for every node, you obtain that twice the sum of all the x's is equal to twice the cardinality of V. And therefore, this equation is then obtained by dividing by 2 such a sum. Great, now this is the system I want to consider. In order to construct a Lagrangian relaxation, now I have to choose which are the complicated constraints that I want to bring in the objective in the Lagrangian relaxation. And the choice that we make at this point is to pick as the complicated constraints all the degree constraints except for the one corresponding to the node 1. For some reason, I want to keep these very specific degree constraints among my constraints. So far the problems as it's written still gives me Zi. Now let's write down the Lagrangian relaxation, which will give me instead ZLR. Here it is. As promised, I kept among my constraints the degree constraint only corresponding to node 1. I still have all my subtour elimination constraints and I have the redundant equality that I have added. Then I have brought in the objective the penalization term corresponding to all the degree constraints for every node except for node 1. A key observation is that at this point, the inequality that was redundant before is no longer redundant for the current Lagrangian relaxation, because I don't have all the other equalities that used to imply such a constraint. Now, the set of feasible solutions to this Lagrangian relaxation is an interesting combinatorial object. In fact, in this observation, we're going to show that the feasible solutions of the Lagrangian relaxation are precisely the incidence vectors of 1-trees. What are 1-trees? Let's see their definition. A 1-tree in our graph is a subset of edges such that, first, the edges in T that do not touch the node 1 forms a spanning tree in the graph obtained from G by removing the node 1. And secondly, T must have exactly 2 edges incident with node 1. Note that in this definition we are considering completely separately the edges that are not incident with node 1 and those that are incident with node 1. Now let's prove this observation. The idea to prove this observation is very simple. The definition that we gave of 1-tree treats separately the edges that are incidents to node 1 and those that are not. So we should obtain the same thing in our inequalities. Therefore, we want to partition the constraints of the system in such a way that one of the two partitions only contains variables corresponding to edges incident to node 1, and the other partition only contains all the other variables, therefore those that are not incident to node 1. So let's have a look at currently what we have. Well, the first constraint definitely deals only with variables incident to node 1. Our subtour elimination constraints, on the other hand, only deal with variables that are not incident to node 1. That's because we're only considering subsets of nodes that don't contain node 1. So let's highlight this in a different color. Finally, the last constraint that we have contains all variables. And so this is exactly the equality that we need to change in this formulation. And how are we going to do that? Well, we're going to remove from it the inequalities A, so the ones highlighted in yellow here, and obtain in such a way an equation containing only variables of edges that are not incident to node 1. Let's do it. In our system, we can replace constraints C with the one obtained subtracting A from C, which is sum for E in capital E minus delta of 1 of xc equal to cardinality of V minus 2. And let's call this equation C prime. We have achieved now our goal because constraint C prime is expressed only in terms of the variables relative to edges of G minus 1. So essentially I can highlight it in orange. So now we can write our feasible set as a product. Let's do that. The set S of feasible solutions of the Lagrangian relaxation equals S1 times S2, where S1 and S2. So S2 will be our orange set, while S1 will be our yellow set. So S1 is the set of binary points in dimension delta of 1 that satisfy only A, which, if we go back, is our only yellow equality, while S2 is equal to the set of x's in 0, 1 to the E minus delta of 1, such that the orange inequalities, which are B and C prime. At this point, we can analyze these two sets separately. So let's look at the yellow one. So these are all the binary points that satisfy only A, this yellow equation. And so it is exactly the set of incidence vectors of subsets of delta of 1 of cardinality 2. On the other hand, what is S2? The set S2 satisfies the orange equation C prime and all the inequalities B. And we have seen this system before because it describes the spanning trees in G minus 1. Let's write it down. S1 is the set of incidence vectors of subsets of delta of 1 of cardinality 2. And S2 is the set of incidence vectors of spanning trees in G minus 1, which is exactly our definition of one tree, and so this concludes our proof. Back to the slides. We have just shown that the feasible solutions of the Lagrangian relaxation are the incidence vectors of one trees. Therefore, for every given lambda in our Lagrangian relaxation, solving such a relaxation consists in finding a one tree of minimum cost, where, once again, the cost depends on lambda. Now, the definition of one trees we've seen essentially treats separately the edges incident to node 1 and the other edges. Therefore, in order to compute a minimum cost one tree, we can separately optimize these two structures. So here's our algorithm. We compute a minimum cost spanning tree, T prime, in G minus 1, and then we pick the two edges E prime, E double prime, incident with node 1 of minimum cost. Then our minimum cost one tree is the union of T prime and E prime, E double prime. Clearly, step 2 can be done in linear time, and regarding step 1, we have seen that such a minimum cost spanning tree can be obtained, for example, with Kruskal's algorithm. We're also in a position to fully characterize what is called the one-tree polytope, which is the convex hull of the incidence vectors of one trees. In the next proposition, we will show that the feasible region of our Lagrangian relaxation is in fact a perfect formulation. We're going to show that the one-tree polytope of G is described by the standard linear relaxation of the constraints in the Lagrangian relaxation. Let's show this. In the statement here, I have explicitly written down the standard linear relaxation of the constraints in the Lagrangian relaxation. In fact, note that it's the same exact system except for the inequalities xc between 0 and 1, which replace the binary constraints that we had in the formulation. Well, there's not really much to do in this proof. Essentially, I'm just going to use what we've done in the observation. I'm going to use the theorem that we saw in chapter 4 that characterizes the spanning tree polytope, and I will leave the rest as an exercise. The proof, like the one of the observation, we want to partition our constraints into two sets. One set will contain only the variables corresponding to edges incident to node 1, and the other partition contains all the other variables. So let P be the polyhedron described by the standard linear relaxation of the constraints in the Lagrangian relaxation. It follows from the proof of the observation that P can be written as the product of polyhedra P1 times P2, where P1 is the set of vectors with components corresponding to edges in delta of 1 and in the interval 0, 1 that satisfy only constraint A, and P2 is the set of x in, again, 0, 1 in the space of E minus delta of 1 such that B and C prime. So this is exactly the same thing we've done in the observation, but this is the corresponding linear relaxation of the sets S1 and S2 that we saw there. And now we just have to study separately P1 and P2. It is easy to see that P1 is the convex hull of S1. Prove it. This is an exercise for you. And by theorem 4.25, P2 is the spanning tree polytope of G minus 1. That is P2 equal to conv S2. Therefore, both P1 and P2 are integral polyhedra, and so is their product, P equal P1 times P2. And this concludes our proof. Let's go back to the slides. We've just shown that the 1-tree polytope of G is described by the standard linear relaxation of the constraints in the Lagrangian relaxation. Therefore, together with our corollary 8.5, we now know that the bounds given by the Lagrangian dual, so ZLD, and the bound given by the Dantzig-Fulkerson-Johnson linear relaxation, ZLP, coincide. Note that, as opposed to the general theory that we introduced in this chapter, where our original problem was a maximization problem, for our example of the traveling salesman problem, our objective is instead in minimization form. Therefore, all the bounds that we obtain are lower bounds, and in particular, the Lagrangian dual is defined to be the best lower bound. Therefore, we maximize over lambda instead of minimizing as we did in the general theory. So essentially, all max and min are just exchanged. So in this case, ZLD and ZLP coincide, where generally ZLD can be a better bound than ZLP. So in a sense, this is a worst case scenario for ZLD because it's as weak as it can be. However, let's take a moment and discuss separately the Lagrangian dual and the LP to understand at this point the pros and cons of both these problems. So let's start by ZLP. So first, this is just a linear programming problem. However, it has an exponential number of constraints, and we know how to separate them in polytime. Due to the ellipsoid algorithm, we then know how to solve this linear programming problem in polynomial time. So from a theoretical perspective, we can obtain ZLP efficiently. However, from a practical perspective, not that much, because at the end of the day, the ellipsoid algorithm is not very fast in practice. And besides, if you want to implement yourself and solve this problem without using any external software, you have a lot to code, because you have to code first the separation algorithm and secondly the whole ellipsoid method. On the other hand, what about ZLD? Well, if we want to talk about the Lagrangian dual, let's first talk about the Lagrangian relaxation. Well, we've discussed that for every lambda, the Lagrangian relaxation can be solved extremely fast. In fact, the thing that takes the most time is solving a spanning tree problem that we can do with Kruskal algorithm. Besides, this can be done efficiently also in practice because Kruskal's algorithm is just few lines of code. On the other hand, you want to find the best bound given by ZLR lambda, therefore you want to maximize over any lambda greater than or equal to 0, and this is not so trivial. On the other hand, something that you can do in practice very quickly that will not necessarily give you ZLD, but maybe a good approximation, is just generate a bunch of lambda non-negative and solve the corresponding ZLR lambda and pick the best among them. Of course, this will not be the best among all possible ZLR lambda, but just over a finite subset of them. So it will not be quite as good as ZLD, but in practice, maybe this serves as a good approximation of ZLD. So this concludes our discussion on the Lagrangian dual.